So, ladies and gentlemen, today we will discuss about a method or scheme to generate amplitude modulated signal. As we can see, the expression of an amplitude modulated signal indicates that we have to generate two parts. One is carrier signal part and another part that is carrier signal multiplied by the message signal. With this motive, we have considered a circuit where carrier signal and message signal is added and then passed through a diode, and voltage is taken across a resistor, which is again passed, the resultant signal is passed through a band pass filter, and we get the final output. So, at the input of the diode, where we are getting CT plus MT. When this is greater than 0, diode conducts. When it is less than 0, it doesn't conduct. Here we are considering that this is ideal diode. So, what is happening here? Here is some switching case happening. What we see, when CT plus MT greater than 0, diode conducts. When CT plus MT less than 0, diode doesn't conduct, due to the cause of forward bias and reverse bias respectively. Therefore, we can write the expression of the voltage across the resistor indicated by V1T as CT plus MT multiplied by a waveform which is on for half period and another half period is off, and it is shown by WT on the right hand side. You can see WT. Okay, this is our WT. Diode is on, indicated by this. Diode is off, indicated by this one. Now, if you carefully consider that the frequency of the carrier is very high than message signal, therefore when CT will be, or the switching of the diode will mainly depend on the frequency of the carrier signal, and it will be very much close or maybe equal, or rather tending to equal. This switching the switching frequency will be close to the carrier frequency. Okay. Therefore, this switching indicated by this waveform may be considered the frequency, that is 2 phi into 2 phi f, that is 2 phi into 1 by t time period. We can approximate it as the omega c. This is the waveform of this switching. We are approximating it to omega c, frequency of carrier, as switching mainly depends on the carrier or carrier frequency. Okay. Now, so we can write that V1T is CT plus MT into WT, where WT is this. We have already calculated the Fourier series of this waveform. What it was? Half plus 2 by pi cos omega ct minus 1 by 3 cos 3 omega ct, and so on, plus 1 by 5 cos 5 omega ct, and so on. So, therefore, if we write omega t in Fourier series form, we get this. Ct here in this expression, Ct is replaced, Ct is written as AC cos omega Ct. So this is half into Ct, that means half AC cos omega Ct plus half into Mt plus 2 by pi cos omega Ct into Ct. Okay, that means here cos omega Ct, that means cos square omega Ct, and this 2 by pi Mt into cos omega Ct, and several terms. Several terms means it is cos omega ct into cos omega ct, that means cos square omega ct. It is mt into cos 3 omega ct, and so on, several components having frequencies higher than omega c. Now, if we see the expression, what we need this AC cos omega ct. Okay, there may be some scalar multiple, it doesn't matter much, we can adjust it. And another is mt cos omega t, mt cos omega t. And here is the term, say cos square omega ct, or cos omega ct into cos 3 omega ct, that will give us cos 2 omega ct and cos 4 omega ct. This term we don't need. We also don't need only the message signal. What will be the benefit if we send only the message signal? As its power is very low, after going some distance, it will die down. And this is not derived from this expression also, that cos omega ct part, and another is cos omega ct multiplied by mt. Okay. So what we need, we have to pass this cos omega ct and m cos omega ct, and the other part should be eliminated. Therefore, and it is also evident from the Fourier transformation or representing it in the frequency domain. What we see, mt, that is m omega in frequency domain, cos omega ct part, mt cos omega ct part, m omega minus omega c, m omega plus omega ct. Okay. So we need this part. Okay. That means we want to pass cos omega ct and m cos omega ct. Cos omega ct and m cos omega ct, we don't want to allow cos 2 omega ct, cos 3 omega ct, cos 4 omega ct. This term generated by multiplying this part with that part. We don't need them. Rather, we don't want to. We want to eliminate them. Therefore, we have to use a filter. Which type of filter? The requirement is you pass the signal with a certain frequency at the center. Therefore, and this is non-zero. The center frequency should be non-zero, as we can see. So what we will employ? We will employ a bandpass filter. What will be the bandwidth? What will be the center frequency? The center frequency should be what? Omega c. And what should be the bandwidth? Bandwidth should be, what is here? Omega c plus omega m. This is omega c minus omega m. So the bandwidth should be 2 into omega m. That means 2 into bandwidth of the message signal. Therefore, we will pass this through a bandpass filter with the center frequency omega c, bandwidth 2em, and we will finally get this 2 term. That means our amplitude modulated signal. Thank you.